Okay. So, okay. Welcome everyone to the third lecture of Mahir Bilen. I guess we can just start Mahir today.
Okay. Yeah. So I wanted to point out one fact about simply connectedness issue. So we will call. So to be very clear from the beginning, I will call a group an algebraic group G is called simply connected. If every covering homomorphism G tilde to G with finite kernel is an isomorphism of algebraic groups. Okay. Now, so for example, SLN, the classical groups, symplectic group over complex numbers, spin groups are all simply connected. It is a good exercise to show that already the one-dimensional torus is not simply connected. So this sounds very obvious from a real topology viewpoint. Indeed, the theorem, there is a theorem that says that if the underlying real Lie group of a complex algebraic group is simply connected, then G itself is also simply connected in this definition above. Is simply connected as above. There are some confusing statements in the literature. I'm not going to tell what, but in the notes, in one of the theorems that I typed, included in the notes yesterday, I stated a theorem based on a paper which the theorem seems to be modified. An assumption is missing there. So I will correct the notes and repost them with giving reference to a beautiful explanation that I found in Stock Exchange yesterday. It is funny because that paper is such a classic paper and the explanation seems to be written only in 2016 or 15. The correct, absolutely correct statement. Even though I'm pretty sure experts were aware of that, but at any rate, let me continue with today's lecture. I just wanted to point out this fact about simple connectedness. This is related to our next discussion in the following sense. So I'm going to soon define the combinatorial ingredients of the representation theory or structure theory of reductive algebraic groups. These things are called root systems. And then, of course, we have the rational representations of these objects, and they They are essentially irreducible ones are parameterized by certain characters. So we have the character lattice, we have the weight lattice, right? We have the root lattice. So the interactions between these lattices is actually measured by the fundamental group of the underlying algebraic group. So this is quite relevant to that discussion also, even though it is not essential to use this for the moment. Okay, so let me move on to the concept of a root system, and then I would like to discuss fundamental weights, the weight lattice, and then maybe I'll come back and make that comment in relation with this, what I explained just now. So let's start with the Euclidean vector space, root systems. So let's denote by E a Euclidean vector space. This means it's a finite dimensional vector space with inner product on it. And for every vector, we know this from calculus. If this is a vector, is any non-zero vector, then we can associate the reflection operator with respect to hyperplane that is orthogonal to alpha. Reflection, linear operator with respect to the hyperplane x of alpha that is orthogonal to alpha. So we can certainly write this in coordinates, and the following notation will be helpful. This is sort of a question that I like to ask my calculus students time to time. In R2, given a vector, how do you write down that linear operator explicitly? Some people get it, some people don't. But anyway, of course, nobody writes as conceptually as follows. So let's say our inner product is denoted by these parentheses. Okay, so I'm going to define this new pairing between vectors in E, and it is defined as 2 times the product of beta and alpha divided by alpha and alpha. So set where alpha is non-zero. Okay, then in this notation, our operator becomes, then S sub alpha can be explicitly written as B beta minus this coefficient defined by this number, that way, for every beta in E. Okay. So let's keep this in our pocket. Now I'm going to define the root systems. Now a finite set of vectors in E, so a finite set of vectors, let's call this finite set R, this is in E, is called, I also want them to be non-zero, I guess, a finite set of non-zero vectors is called a root system if it spans the whole vector space. And then for every element of this set, the reflection operator permutes this finite set. And now finally, I want these coefficients to be integers for every pair of vectors from this set. Okay, it's just a bunch of vectors that has symmetry, is some sort of internal symmetry with respect to linear operators that they define. That's what it is. It's a spanning set of E with some internal symmetries, with some, this is integer, with some integrality properties. Okay, now, so sometimes in the definition of a root system, the following requirement is included. If alpha is in R and C is a real number, the inclusion implies that C is plus minus 1, then this root system is said to be a reduced root system. So reduced root systems are critical for semi-simple groups, but for the time being, I'm not going to include this reducedness assumption in my axioms. And then there is one more definition. A root system is called indecomposable. And some textbooks call this irreducible. If it cannot be decomposed into a disjoint union of two sub root systems whose roots, these are the elements of the root system, are orthogonal to each other.
Just one question. The condition number 2 says that all elements of this R lies in the alpha per, right? All these vectors lie in alpha per, all of them. Collection of these vectors. Number 2, yeah.
Yes. So they lie in the root system. For every root.
For every root. Oh, I see. For every root.
Yeah. For every root, the associated reflection operator permutes R.
So that means R is in the alpha per, right? Because that was projection into alpha per.
No. It's not projection. It is a reflection. S alpha is the reflection.
Oh, reflection.
Yeah.
Okay.
So it's a reflection operator. You're right. If you take it to be projection, then it would be different. Yeah. So it flips everything symmetrically with respect to hyperplane of alpha. Now, so okay, so indecomposable means that I cannot write R as disjoint union, where alpha from R1, beta from R2. So we don't want to have this. So if this happens, then I mean, if R can never be decomposed into two sub-root systems where the roots of the individual partition parts are orthogonal to each other, then it is indecomposable. I wanted to move it in the composable adjective because, you know, we talk about irreducibility too often, so I don't want to overuse it. Now, a little fact, an easy fact is that, going back to here, if for any root system, if alpha and C alpha are elements of the root system R, then here C is a real number, alpha is from R, then the C can be plus minus 1, plus minus 1/2, or plus minus 2. So these are the only possible scalar multiples of a given root that we can see in a given root system. If it is reduced, we only see plus minus 1. Okay. All right, so now let me draw some well-known pictures for root systems having a few vectors in them. I'm going to focus on rank 2 root systems. I will explain what rank means. Well, first of all, we have this well-known 6 vectors with angles 60 degrees between them. This is a root system labeled with A2. And then we have the square vectors. So these are vectors that goes to the middle points or corners of a given square. This is labeled usually by B2 or C2. And now we have this G2 guy. It has 6 short roots. It's like A2 in it. And then we have additional 6 long roots that are obtained by sums of these short roots. And then we have this plus sign. This is denoted A1 cross A1. And then finally, we have this extended version of B2. So I should say enlarged version of B2, but then we put these little middle guys here for the diagonal. And this is sometimes denoted BC2, simultaneous. So here I wrote B2 is equal to C2, but this is literally BC2. This is the labeling. And these 5 figures essentially is the list of all rank 2 root systems. Here, the first 3 are reduced and indecomposable.
So the lengths of these vectors are forced by this condition, right? If alpha is in there and C alpha is in there, then C is equal to 1, something like that.
Yes, so indeed, relative lengths are, of the vectors in a given root system but relative length.
Yeah, red lengths. It's a result of that condition, right? Multiply the root with a C, then to be
C means plus minus one. Yes.
Something like that.
Yeah. Yes. And then this is reduced but decomposable. And then this is non-reduced, but indecomposable. Okay.
Remind me what reduced was. I already forgot.
Reduced is coefficients are plus minus one. Plus minus one.
No, but you said then there's a two collection of them. If it's a union of two.
Oh, that's indecomposable.
Yeah,
decomposable means we can decompose it into two subroot systems.
okay.
But the point is that vectors from different subroot systems have to be orthogonal to each other.
Okay.
Not just separating. Otherwise, it may look like B2 could be written that way as a union of two subroot systems, or G2 would look like that. But it is the condition that they are mutually orthogonal is also important.
Okay.
Now, so the reason I didn't want to impose this reducedness condition is because later on we will attach root systems to homogeneous spaces, not just to simple, not just to reductive groups. And often turns out that the root system of a homogeneous space is actually non-reduced. Okay, so now actually we can define this, we can arrive at this axiomatic study by purely studying characters of the algebraic groups without going to these explicit vectors. And for this, let me just quickly review this. Now, so let G be a reductive group. Remember, this means that it doesn't. Its unipotent radical is trivial. It has no normal unipotent subgroup, non-trivial subgroup. Now, I'm going to fix a maximal connected solvable subgroup. Fix a Borel subgroup. B. This is a maximal connected solvable subgroup. Such subgroups already appeared in a fundamental way in the definition of reductiveness. Maximal connected solvable subgroup. And then I'm going to fix a maximal torus of G. Let's denote it by T. And let's insist that it's contained in B. By the way, I should say here, tori are commutative, in particular solvable. Therefore, they will always be contained in one of these Borel subgroups. So every tori is contained in some Borel subgroup. So I might as well fix the Borel subgroup that contains a given maximal torus. Okay, now, now remember a one parameter subgroup of any group G, algebraic group G, is nothing but an algebraic group homomorphism from the multiplicative group of the underlying field. Let's work with complex numbers. So C star, one-dimensional torus, and it will go to into our group G. In fact, I'm going to take it to be a torus. It's the image of a torus. It's the same simple guy. So a one-parameter subgroup is just an algebraic group homomorphism from one torus into our group G. Let's say it lands in T. I'm going to call a character. Okay, so this is a node. A character of T. A character alpha of T. Remember, character means it's just an algebraic group homomorphism in the opposite direction. So it goes in the other way. Okay. A character alpha of T is called a root relative to T, the root of G relative to T, if there exists a one-parameter subgroup phi such that when I conjugate the image of this one-parameter subgroup at an element C, I get again something in the image of this one-parameter subgroup scaled by the torus value. I mean the character value.
Just to make sure I'm not forgetting the definitions. So these reductive things are far from semi-simple ones because they contain abelian subgroups. Is that correct?
Yes, correct.
Thank you.
Yeah. But what's happening here is essentially you can show that this construction ignores the unipotent, any normal unipotent part, because if you take a character of G, well, actually of T, maximal torus of G, in a sense, you can factor out the normal unipotent part, and it does not affect any character of T. So if you have a normal unipotent subgroup, what am I trying to say? No, that's not what I'm trying to say. I wanted to explain the fact that actually this construction doesn't see this stays the same if you pass commutator. Long story short, you can simply start with the reductive group G, take the commutator subgroup, and the root system will remain the same. So yeah, so think of the example of GLNC and SLNC. So they have same root system. Yeah. So okay. So let's continue. Now I'm going to call. So this is a very quick way of introducing root systems in the group theory context without referring to the discrete combinatorial object, which usually is constructed through the Lie algebra of the Lie group or algebraic group. But here we are defining things internally, just using group theoretic characters. Of course, this already should alarm us in the following sense. Character not every root is a character. Sorry, I said it the other way around. Not every character is root. So there is some sort of a relationship between characters and the roots. I should make this a little bit more precise by saying that now that we have these spatial characters in on our T, we can look at their, remember, character group was a free abelian group, finitely generated free abelian group. It was from yesterday's lecture, right? That was one of the propositions. So
can you move the top of this page a little bit so we will remember?
Oh.
Yeah. So
Sorry,
this
I
is,
can't
this
tell
equality,
what you would like to move.
This equality is true for some alpha, right? And if there's a phi such that conjugating phi of this equality about phi, definition of phi.
So I take a character, alpha, and then I call it a root if there exists a one parameter subgroup phi satisfying this equation.
Okay. Yeah. You choose special characters to call them roots.
Yes. So certainly there are finite many. Well, it's not very obvious from the beginning, but there are only finite many roots. So there are only finite many characters that can be root. But the next thing that I wanted to tell you is that even if you take the subgroup generated by roots in the character group of T, there is some, often there is a discrepancy between that lattice and certain other characters that I'm going to define in a second, and they will naturally correspond to irreducible representations. So far what I wrote here is just some naming of some certain characters of T, and I call them roots. But then you can check that the collection of all roots that I defined this way obeys the axioms that I defined previously. So you may ask, where is the Euclidean space? Well, the Euclidean space in this case is just take the character group of T, which I will denote this with this unusual notation, T. So this is the, let's use T to denote the group of algebraic characters of T. This is a free abelian group of finite rank. And in fact, yesterday we learned that it is nothing but we can define it internally as the group of invertible elements of the global sections of the structure sheaf on T mod constant functions. Now, because it's a free abelian group, I can take the vector space generated by it, and this is our Euclidean space with well, I need to explain some inner products here, but let me postpone it for a second. So you can always put an inner product and then fix it a little bit so that it becomes a nicely behaving inner product with respect to those reflection operators.
So to remind myself what we did yesterday, so OT here is just like E of G when G is T, right? You define it E of the algebraic characters.
Right. So yesterday we observed that. Yeah. So we observed that if you start with any algebraic group G, you can look at it. It's an algebraic variety you can look at its structure shift OG, and then look at the global sections of this. So if G is an affine algebraic group or affine algebraic variety, this is nothing but coordinate ring of G.
And you took the invertibles.
Yeah, and then we took invertible elements in that section. So the global sections contains constant regular functions too, and we looked at its quotient.
I see. So when G is, if you replace G is with the maximal torus, then this is your definition of Ö of T.
Yes, correct.
Thank you.
Yeah. Now, okay, so this is a free abelian group of rank R, so it gives us a Euclidean space, and then we can treat now characters as elements of this Euclidean space and run the previous axioms and check them and show that this actually collection of characters that we define this way indeed satisfies those three axioms that I introduced. So these guys really form a root system.
So when you draw like this, you draw a picture of the characters after you tensor it with R, and then among them you will choose roots, right? With your condition. Only some of them will be.
Correct. Yes, correct. Yeah. And so this was a really fast way to introduce root systems without worrying about Lie algebras or anything like that. I should say maybe introduce weights here. So so now in E, in this Euclidean vector space, we have we can so let me say it in okay. Now so given so given a root system, R that lives in our Euclidean vector space E, we can introduce the dual root system in the dual vector space by taking the duals of the elements of R. So we have this guy that lives in the dual space. Now, if you remember, I said something vague about this inner product on E. If you start with any inner product on E, you can always turn this into an invariant inner product, invariance with respect to the group generated by reflections of R. So let's assume that. Assume that this is a W invariant inner product. Where W is the group generated by S alphas or S betas. these are our reflections as subalphas. Sometimes this is called the while group of the root system R. Now, using this inner product, we can identify E with E star. Okay, then we have under this identification a dual of a root looks like this 2 times the root itself and divided by length. Okay, so this is now this guy will be called the co-root. Okay, now so co-roots also form a root system in the same Euclidean space. So if I scale my roots according to this, I'll get another root system. So previously I showed you some pictures of rank 2 root systems. It would be a good exercise to check which of those root systems are isomorphic to their duals. Some of them are like yeah, so maybe rank 2 is too small. Maybe you have to look at rank 3, but it's a good exercise to check which of those, at least reduced indecomposable root systems, are dual to each other. So now what I will define now is another important ingredient in representation theory. So I will call a vector omega from E. I'll call it a weight if this is integer, if this pairing is an integer for every root alpha. Right, so these co-roots are elements of E, and then remember I had that convenient pairing I introduced before. I want to look at those vectors that have this integrality property with respect to pairing with the co-roots. Okay.
And weight can be root.
Not really. I'm hesitating because maybe in rank 1 I didn't think about it. In rank 1 case, they may all yeah, if it is rank 1, you may call it a root indeed. Okay. So in general, no. The answer is in general is no, but you may have some like extreme case that the answer might be yes. Okay, so now I wanted to make this comment now. Now in E, we have the root lattice spanned by the roots. And we have we can certainly look at the lattice generated by weights. Now, so let's it can be checked that I always the weight lattice contains the root lattice. So now this will also answer your question in a good way. So by the way, these are the ranks of these lattices are full. They have the same rank. Therefore, the quotient of these abelian groups is torsion, and called the fundamental group. Torsion is again. I want to assume focus on semi-simple case. Assume that G is semi-simple.
But wait a minute, I thought we were playing with reductive.
Yes.
In
there. Yeah, so I just hesitated for a moment because what happens if I add a torus factor and then I guess then E, I wouldn't use that component of E. Okay, yeah, so yeah, because I'm restricting myself to this particular E, E is spanned by the root system, so okay, I'm gonna delete this thing, reductive. The quotient of these abelian groups is torsion and called the fundamental group of the root system.
So, by the way, when you say root lattice, weight lattice, you mean Z-linear combinations of those elements, right?
Z linear.
Yeah.
Like they generate a free abelian group in this vector space. That's what I mean by lattice.
I see. Yeah.
And the number of generators is the dimension of the vector space. And this fundamental
question, weight lattice is determined by the root lattice, right? If I give you root lattice, from there, combinatorially, you can compute weight lattice. Is that
yes,
right?
Correct. Yeah, essentially, this definition shows that we can construct weight lattice by these assumptions, and we can explicitly calculate the generators of the weight lattice. In fact, let me quickly review that construction to explicit description. Now, to do that, I need to tell you about the basis of the root system. So now, given a root system R in E, we can always find a hyperplane, since this is a discrete set, separates this passes through the origin, a hyperplane through origin. That separates R into two equal cardinality pieces. Denoted by R plus and negative of R plus. Okay. It's just a matter of choice. Call one of them positive roots.
But they don't have to be symmetric like that, right? If you take an arbitrary hyperplane, separate it in two, and one side might be different looking than the other, right?
No, it will always be symmetric. It is because the root systems are extremely symmetric, symmetrically positioned vectors.
Okay, I see.
Any hyperplane that doesn't contain any roots will have this property.
I see. Okay. Good to know.
Yeah. So call R plus a set of positive roots. It's a choice here. Now also notice that there is a continuous family of hyperplanes that we can choose and get same splitting. In fact, that continuous family of hyperplanes essentially it looks like a cone. I mean, if you can visualize it for our rank 2 examples, for instance. Here, choose this H, for instance, right? Then this splits this thing into two parts. But I can move this H in this range. There is some freedom to choose H in this region and get same splitting. So these regions are anyway. I will talk about these are sort of like closely related to notion of a chamber, but I'll come to that later. So let's call this a set of positive roots. Now, in here in R plus, for instance, I can take we can take a maximal subset S with the property satisfying the property that the elements of S cannot be written as a sum of two other elements from R plus. So to speak, indecomposable elements of R plus. Let's call these guys simple. The elements of S are called simple roots. Elements of R plus are called positive roots. And then an easy thing to verify here is that S is a vector space basis. Basis for E. And okay, and so there is also a conceptual way of relating this set S. So far in this description, I did not refer to the Borel subgroup, but essentially this choice of splitting is canonically attached to a choice of Borel subgroup that contains the maximal torus. So this S is uniquely determined by a Borel subgroup that contains the maximal torus T, and vice versa.
We have about 5 minutes, by the way.
Oh, this is terrible, really. I mean, I can't really keep track of time here.
You have all the time. You have more days if you want to.
Yes, but this can get out of control very quickly. So
Why not?
But we have finite time. Now, okay, so we have the basis for our set of simple roots for our root system, and all right, so let me quickly mention how this is related to Borel subgroup once again. So if now, so previously in my so a quick correction. So in my original definition here, remember I made that restriction. So I took my one parameter subgroup to be a subgroup of T here, right? So I want to take this to be G. It's kind of silly. I was a little bit distracted. So please make this correction, otherwise things will be super simple. So this one parameter subgroup that I want to choose, it actually goes into the reductive group G, not to the maximal torus T only. Okay. So going back to that discussion, so now
I'm a little bit worried about this. I'm a beginner in this. You know, sometimes you do the same argument when group is not reductive, right? You define Cartan subalgebra divide with that. There's this construction with roots. So if you don't have if you see even simple group, we have this kind of discussion.
Yes.
So, I mean, what's the difference in here? I mean, in terms of process that you are leading to?
For the difference between reductives and simple?
Semi-simple. When you do the argument with semi-simple things, you have the roots and you have simple roots, etc. Now, all of a sudden here, you're talking about the Borel subgroup in here. In the other semi-simple case, what is the Borel subgroup? It's just the commuting elements?
No, it is the difference is just so Borel subgroup of a reductive group contains that extra adjunct torus.
Yes.
So Borel is maximal connected solvable subgroup. Remember, there was some previous discussion about the how to define reductive groups. That I said any reductive group G can be written as its commutator subgroup, semi-simplified, some connected center mod finite central subgroup, right?
Yes.
So Borel subgroup of G will always have this central subgroup, central torus. So the Z here is the connected center of G, but by definition, a Borel subgroup is a maximal connected solvable subgroup. Because of maximality, it will always contain the torus, central torus. So this Z is part of it. So the difference between the Borel subgroup of G and Borel subgroup of G0 is essentially this central part, central torus.
I see. Yes. Yes. Yes.
So as long as we ignore, and in all that root space calculations, so this, so in my definition, so I just realized this stupid mistake I made, but so we want to replace this by G. So this one parameter subgroup has to go into unipotent. I want to hit unipotent elements in here so that I can define the notion of a root. But all the unipotent elements of a reductive group are essentially determined by the semi-simple part.
Right. And there's also torus in G0 and G, right? There's maximal torus in G and G0.
Yes, there is maximal torus in G0. Yeah. That maximal torus doesn't need to be central. And in fact, it shouldn't be in general, right? I mean, so connected, I should say that if you take a maximal torus in G0, combined with this central torus, they will give you maximal torus of G.
Okay, thank you.
So now, going back to the roots, so those the one parameter subgroups that define that are used for defining the root system in R define unipotent subgroups. I should say one-dimensional unipotent subgroups of G. So alpha is a root, and that's denote the corresponding thing to be use of alpha. By the way, I guess I also want this one parameter subgroup to go from, yeah, so this was a mess. So I want this to go from GA, not from GM. So this is an additive one parameter subgroup. The reason I want to work with these guys is that these unipotent subgroups are just like one-dimensional additive group. And this is called the root subgroup. So now, here is a little proposition. The Borel subgroup B that we started with is equal to the semi-direct product of the maximal torus T that we choose and the unipotent subgroup generated by these root subgroups, but we only use positive roots. So this is the direct explanation of why this splitting of roots in the positive and negatives are related to choice of Borel group B.
T sits inside of G naught, right? T.
T sits in G. So T has so let's denote T naught to be intersection of the commutator of G with T. So this is G naught. So T0 and T are related to each other by the central torus. So T0 cross Z has this natural surjective multiplication map. And this is a finite morphism with kernel isomorphic to Z naught. Yeah, so this also, in some sense, indicates why the fundamental group of G is essentially related to fundamental group of the semi-simple part of the derived part, because connected torus is like I guess I have to be a little bit more careful here, but at least this can be controlled, but the real unknown part comes from G0. Okay, so now I know I'm getting over time. So I defined the weights, weight lattice, root lattice. I didn't define fundamental weights. Fundamental weights are now that I defined the simple roots, let me just quickly define them. So remember we had, so let's list the elements of the set of simple roots by alpha 1 up to alpha L. The set of simple roots. For R. So this is completely determined by the choice of a Borel subgroup. Define omega 1 up to omega L by the equations so these are the weights that has this they pair to 0 or 1 by the simple chorus. And so the weight lattice is, of course, is generated by omega 1. So the weight lattice is spanned by the fundamental weights. Now I call them fundamental weights. Okay. Now the relationship of these fundamental weights to representation theory, since I'm running out of time, I'm just throwing big sentences. So next time I will discuss this in a little bit more detail, but if we take if V is a finite dimensional, irreducible, rational representation of G, then we can look at the torus weights the weights of the maximal torus T, that appear in V. By this, I mean we can view V as a representation of T. T is an abelian group, so V is going to decompose into one-dimensional subspaces, and each subspace is attached to an eigenfunction. Is determined by a character of T, and those characters are called weights of V. So we are looking at the torus weights in V that defines its decomposition into joint eigenspaces when we view elements of T as operators acting on V. Then among all these T weights in V, we can choose a maximal one. There's a maximal highest weight. I should say just highest weight of T in V, and so we can do this for any finite dimensional irreducible representation, and that highest weight, is a non-negative integral combination of the fundamental dominant weights. And conversely, for every non-negative integral combination of the fundamental weights, we can construct a finite dimensional rational irreducible representation of the group G.
What is the dominant weight?
It's part of the name, fundamental dominant weight. Let's call this fundamental dominant. So let's call these omegas fundamental dominant weights. Well, why did I throw this in? If we just ignore this representation theoretic significance, a dominant weight is a weight that can be written as a non-negative linear combination of fundamental weights. It's just the naming of the weights that can be written that way. So going back to the example of A2, we have these 6 vectors, right? Then it can be calculated that omega 1 is here. So my set of simple roots, let's say alpha 1 and alpha 2 are these 2 guys. Then omega 1 will be, you can calculate this explicitly. It is this vector here. And now we have omega 2 here. And then take lattice or the lattice cone generated by omega 1 and omega 2. These are going to be things like that. Any weight, any non-negative integral combination here, A omega 1 plus B omega 2, where A and B are non-negative integers. This is called a dominant weight. So in that sense, omega 1 and omega 2 are the fundamental dominant weights. And this is, let's call this the fundamental chamber.
Go up a little bit on the page, little bit.
Oh,
No, other way. Top of the page. Yeah, little bit. Yeah. Okay. No, not too much. Yeah.
and yeah, so this little cone determines essentially all irreducible represent indexes. It's a better way to say it. Every finite dimensional irreducible representation of G is indexed by one lattice point in this cone.
So the process is we start with alpha, then we take the dual of that, and then take the inverse matrix of that to determine this W's.
Yes.
And then make this call. Am I understanding? Right?
Yeah, yes, correct. Yeah, so all of this data is encoded conveniently in the change of bases matrix, the so-called Cartan matrix. But let's not talk about the two. So next, I wanted to tell you a little bit about the decomposition of G into orbits, two-sided orbits of the Borel subgroup, because as you see, Borel subgroup plays a really essential role. In fact, it's so what I call I didn't get a chance to explain it here, but if you take this highest weight of a given finite dimensional representation can be viewed as the character of the Borel subgroup acting on a particular unipotent fixed vector in V. But so the point is that Borel subgroup plays a very important role. I mean, it just governs the whole theory, representation theory here. So it is not a waste of time to explain the orbits of two-sided orbits of Borel subgroup on G, and that's a famous, very useful theorem called Brouwer-Chevalier decomposition of the group G, and it is naturally indexed by the Weil group of the GT, and then we will discuss varieties that has that type of decomposition into finitely many orbits of a Borel subgroup. And for those, combinatorics works at best, just like here, as we just seen. All of this machinery works fine just because we have finitely many Borel orbits, essentially. And so it's only natural to expect similar striking phenomena happens for varieties that we can act on by finitely many Borel orbits. And that was sort of the theme, the planned theme of my talk for the lecture series. But I think I should really stop. It's like I'm almost 20 minutes over.
Thank you, Mahir, for the talk. Like, are there any questions from the audience? Like in the next two lectures, are you planning to like sort of visit those, like what you taught us today about root systems and?
Yeah. So indeed, it's a good time to have a brief discussion now. My plan was to.
By the way, let me stop recording so we can go for informal discussions if you want.